Hello, good morning, good Thursday morning. Nice to have you here. Day 17, meaning it's another day of Advent of Code. Thank you for joining. Yesterday we did 16 and we managed to solve it within 3 hours, just shy of 3 hours. Was pretty nice. The last part involved using a lot of code. Yesterday's solution was the most verbose I think I have had so far. How many lines of code? 150. It was a lot. So after the stream, I took some time and added some comments and some explanations about what is going on. That hopefully makes it better to understand what the solution is. So in case you're curious, have a look. Let me drop the link of the repository in the chat. Hi Chris, nice to see you here. Today was rough. Are you talking about 16 or 17? Which one? Which is the rough one? Yeah, part 2. I've heard a lot of folks had a lot of code for part 2 yesterday. I'm not sure if there's a quicker way to solve it. There probably is. Folks in that are in the top 100 on the leaderboard. These folks are insanely good. They wrote their own helper libraries and their own. I saw Betaverse has his solutions on GitHub. He has like a his language, the language he writes it in, looks like it's something that he made up himself. If we, for example, look at the first day, this is his solution. Like this, this looks alien to me, but it looks like it's something that maybe he has a custom compiler, and then he kind of like has special meanings for each character to kind of like quicker do common tasks in the language, so looping or getting the last numbers and stuff like that. Not sure. 17 is the rough one. All right, then we better get started because we're gonna need all the time we get today. So that was day 16, and today's day 17. Let's go about it. Wait, let me look at the map. Where are we? We kind of like went back north, different island here. I think we might be on a flight. I think we boarded a flight here yesterday. So let's see. Day 17, Conway cubes. Oh, Conway. Conway's game. I think we had it a few days ago. A puzzle that was similar to Conway's Game of Life. So this might hint at it. As your flight slowly drifts through the sky, the elves at the Mythical Information Bureau at the North Pole contact you. They'd like some help debugging a malfunctioning experimental energy source aboard one of their super secret imaging satellites. The experimental energy source is based on cutting-edge technology, a set of Conway cubes contained in a pocket dimension. When you hear it's having problems, you can't help but agree to have a look. The pocket dimension contains an infinite three-dimensional grid. At every integer three-dimensional coordinate, x, y, and z, there exists a single cube which is either active or inactive. In the initial state of the pocket dimension, almost all cubes start inactive. The only exception to this is a small flat region of cubes, which is the puzzle input for today. The cubes in this region start in the specified active or inactive state. So active is a hashtag, inactive is a dot. The energy source then proceeds to boot up by executing 6 cycles. So every time I see a bold word, that means that's a clue about the puzzle. So I try to like remember active, inactive, and then cycles. Each cube only ever considers its neighbors. Any of the 26 other cubes where any of their coordinates is differ by at most 1. Okay, so each cube only ever considers its neighbor. Any of the 26 other cubes where any of their coordinates differ by at most 1. So I guess in a 3-dimensional space, you have 26 neighbors, is that correct? 9 on the top, 9 at the bottom. That's 18, and then 3 on each side, so that's 6. 18 plus 6 is 24. I'm missing 2 cubes. For example, given a cube at x1, y2, z3, its neighbors include the cube x2, y2, z2, the cube at x0, y2, z3, and so on. Yeah, it's kind of hard to visualize that when you're reading this. During a cycle, all cubes simultaneously change their state according to the following rules. Okay, so we had something like this before. In Conway's, yeah, I think it was day 14 or so? Was also something like this. It was with the seats, with the ferry. Yeah, you sit down at the ferry, and then people would sit down and stand up, depending on the neighboring seats, whether they were occupied or not. If a cube is active and exactly 2 or 3 of its neighbors are also active, the cube remains active. Otherwise, the cube becomes inactive. If a cube is inactive but exactly 3 of its neighbors are active, the cube becomes active. Otherwise, the cube remains inactive. Alright, so these rules, we need to code them a bit later. The engineers responsible for this experimental energy source would like you to simulate the pocket dimension and determine what the configuration of cube should be at the end of the 6-cycle boot process. For example, consider the following initial state. So I guess each character is a cube. This is active cube and that's an inactive cube. And we have a grid that's 3 by 3. But interesting, this is a 2D grid. Even though the pocket dimension is 3-dimensional, this initial state represents a small 2-dimensional slice of it. In particular, this initial state defines a 3 by 1 region of the 3-dimensional space. So I guess this is the first layer that we can see, and then there's 2 more layers behind it. Simulating a few cycles from this initial state produces the following configurations, where the result of each cycle is shown layer by layer at each given z coordinate, and the frame of view follows the active cells in each cycle. Alright, so before any cycle, z0, this is the initial state. After one cycle, we get, oh, so that was the middle z. Alright, so then there's a z in front and a z in back. So this is our z here, changes to this one. And then the z in front is this, and then the z in the back is kind of like that. Or whatever you use, -1 might be back, 1 might be front, yeah. After 2 cycles, wait, the grid expanded? That's interesting. I might have missed that in the description. After 2 cycles, no wait, there's another dimension, there's another layer in behind and another layer in front. And it expanded in both the z and the x as well, and the y. So it expanded in all 3 dimensions by, let me see, so in the z it expanded by 1 in each direction, so that's 2 total. And I think in the x it expanded by 2 as well, and y as well. Yeah, there's 2 extras here on the x and 2 extras on the y. Alright, I missed that in the description, I'll have to read back. After 3 cycles, yeah, we see the pattern, although it doesn't expand this time. That's interesting. 3 cycles leaves the z unexpanded, but the x expands and the y does as well, so only the z is unexpanded. After the full 6-cycle boot process completes, 112 cubes are left in the active state. Starting with your given initial configuration, simulate 6 cycles. Alright, how many cubes are left in the active state after the 6th cycle? Okay, so we get our puzzle input, which is this, a slightly bigger grid. Let's save it in our working directory. There we have it. I'm gonna remove the last line. Yeah, I'm gonna split this to the right so we can have a look while we run the debugger. Although it's gonna be hard to make much sense of it though. This is a problem that's pretty tricky to wrap your head around visually how it works, especially because you're given an input that is a slice of the 3D wall that we're gonna work in. it's really hard to work with that, how to kind of like translate. So we're gonna have to write a program that modifies this each cycle and modifies this in a 3D dimensional grid. But then it's going to be really hard to debug that, because you're going to have to translate what the program does into what the visual representation actually the solution looks like, and that transition is tough. Is for us humans mentally, it's really tough to do that step because you're jumping a lot of steps. There's, like in programming, there's tools to I know, for example, game developers that code in Unity, they have a special IDE to do that. And in their IDE, they have a lot of visual tools to help them figure out how a mathematical equation or an algorithm changes what the user actually what the player sees in a game visually, and they can see that as well. They see the 3D rendered output of their program, which makes it much easier. But we don't have that as web developers in our IDEs, because we don't work that much with visual stuff, especially not like this. But yeah, I'm gonna go over the problem again to see. I missed somewhere that the grid expanded in the dimensions. I missed that somewhere, so I'm gonna go back and read it. So here we have pocket dimension contains infinite 3D dimensional grid. At every integer 3D, alright, there exists a single cube. That makes sense. Initial state of the pocket dimension, almost all cubes start inactive. Almost all cubes start inactive. That's not true. We have a bunch of active cubes here. The only exception to this is a small flat region of cubes. Oh, I see. The flat region which we are seeing. The other, oh, I see. So the actual 3D grid is much larger than this, or infinite. But what we are seeing is the active region, kind of like sliced from the entire grid. The only exception to this is a small flat region of cubes, which is the puzzle input. The cubes in this region start in a specified active and inactive state. 6 cycles. Each cube only ever considers neighbors. What I also didn't understood, any of the 26 other cubes where any of their coordinates differ by at most 1. How does a cube have 26 neighbors in a 3D dimension? Let me think. So there's the bottom y, which is 9, bottom top y, bottom y, another 9, so that's 18. And then we have, oh, I see, and then we have 2 rows of 3 on each x side, so that's 6. 18 plus 6, 24. And then we have a single one in front and a back, 26. All right, I understood that. For example, given the cube, all right, during a cycle, all cubes simultaneously change their state according to the following rules. Let's read the rules again. If a cube is active and exactly 2 or 3 of its neighbors are also active, the cube remains active. Otherwise, the cube becomes inactive. So the cube becomes inactive if it doesn't have 2 or 3 active neighbors. And then an inactive cube, but exactly 3 of its neighbors are active, the cube becomes, okay, an active cube becomes active if 3 neighbors are active. Otherwise, it just stays inactive. That's pretty clear. Confusing phrasing, yeah, definitely. What's Bevy? Is that a library in Rust or something, an IDE I talked about earlier? Dun, dun, dun. I saw you solve some of the stuff in Rust. I wish JavaScript had useful libraries like those. I don't remember exactly what you were using, but you were able to use a library that did a bunch of stuff out of the box, and I was like, oh, that would be really cool if JavaScript had that. Game engine, Bevy engine, interesting. Let me have a look. Let me have a quick look here. Bevy engine, data-driven game engine. Oh yeah, could be something useful if you're already familiar with it. Yeah. Rust has cool stuff. I feel like JavaScript misses on that. But because I guess is Rust used a lot in web development, or is it more stuff that is more performance sensitive, like games and maybe graphical design, stuff like that? Because I believe in terms of performance for web development, it might be overkill. Graph library, yeah, I think it was that. Can't remember. Yeah, can't remember which day it was. I think it was around day 10. Not sure. So where did I miss? Oh, I see. So the reason, so the actual grid does not expand. What does expand is our own view of the grid, because the active cubes kind of like start expanding out. So that's what's going on. I understand it now. All right. So anything else I might have missed in the puzzle description that might be essential to solving this? All right. Even though the pocket is three-dimensional, state represents 2, 3, 3, 1 region, Z0. So, oh yeah, I mean, since it's a infinite amount of, since the grid is infinite in all directions, then with the slice, our puzzle input, what we start with is going to be Z0. You can like assume that, and then we'll have to expand in each sides. We'll have to figure out which side to like also consider. Depending on how the cubes are expanding, how the active cubes are expanding out. So we might end up with like -10, but just +4 in the Z dimension. That depends. Although it looks like it's expanding, it might be expanding in all dimensions kind of like proportionally, or at least in the same dimension. In the Z dimension. Yeah. All right. So that's that. I think I have got it now. This is our puzzle input. We are gonna have to. So what's the answer we're looking for? We need to count the active cubes after the 6th cycle, and there can be. This is one slice of the layer, and there's gonna be more slices of that layer as well. This is definitely tough. This is already tough, like just wrapping your head around it, let alone program it. So looking at the puzzle input, I guess we go through each cube. First of all, we'll have to we could like create a grid. No, let's go through first every cube. CLI apps, speed up node programs. Oh, that's interesting. Or compile to WASM, speed up browser stuff, etc. is fun, but it doesn't replace JavaScript, especially for UI stuff. Yeah, so it seems like a language that you can use. On those unique edge cases when you need that extra perf boost that JavaScript can't provide you. Then you tap into Rust, you kind of make a library perhaps, or you separate that special business logic out of your JavaScript, put it into Rust, and then import it from Rust in JavaScript, and then let Rust handle that. Kind of like as you would optimize an app by maybe spinning up a separate worker thread process for a particular CPU intensive calculation, like resizing an image or something like that. That's what you would do with Rust. You would say, okay, we can't do this in JavaScript, it's much efficient in Rust, let's do that in Rust, and then import it. Yeah, interesting. Yeah, I've heard a lot of buzz about Rust going on. Yeah. How does it compare with Go? I'm not very familiar. Is Go something completely different in that case? because both seem kind of like, both from my JavaScript perspective as a Node.js developer, both seem two languages that are really cool, lower level, really performant, but I fail to grasp how they're different, how maybe they do something entirely, something else, not sure. After all cycle. So we're gonna have to loop through each one of them and then kind of look at all the neighbors and count the active ones. How are we gonna keep track of? I'm thinking of 3-dimension. How can I keep track of cubes? And we have a slice here. We're gonna put this in a 2D array, and then we're gonna expand that array in the Z dimension. So it's gonna have to be a 3D array. How do you? I'm gonna Google that a little bit. 3D array, JavaScript. What does that even look like? I never had to work with 3D arrays, I think. Oh, this is a nice tune. So it's just another layer. So the first one, I guess, represents, I would go with the first one representing the Z dimension, the second one representing the Y, and the last one the X. So let's try and kind of like const grid. Let me try and see. So this will be like the Z, a Z, slice of Z, and we're gonna have another one here. And then this slice of Z is gonna be this, what we have here. So that's gonna be Y's, a bunch of Y's, which we can, copy to the bottom. And then inside of here, we're gonna have another array with, no, we don't need, how many arrays do we have? 1, 2, 3. Yeah. So it's gonna be the kind of like the dots and the hashtags, kind of like this. So here we have our. So when we need to get this one, we do grid in the 0 dimension, in the 0 Y at 0x. Kind of like this. Is this what it's gonna look like? So then we kind of need to parse our input and place it in the Z on Z0. But the Z is gonna expand both in a minus and in a plus, and you cannot put an element in grid -1 in array. So we'll kind of need to perhaps put it on grid 100, just to give us the margin in the Z space, so that we don't go in the minus. That's kind of like the trick that I'm thinking of. And then we're gonna have a bunch of empty Z's in here, kind of like that. 100 of those, and then we're gonna have our input in here. And yeah, and then considering the rules, we're gonna have to like subtract 1, get all the neighbors. There's gonna be some logic in getting all the neighbors, and counting them up should be easy. We're just getting all the neighbors for a specific cube in a 3D grid. That's gonna be where most of our time is gonna go. And then changing that, and then looping over the grid as well. We're gonna have to, on each iteration, we're going to have to loop over the grid. But since the grid is infinite, we don't actually want to loop over the entire grid. We only need to consider the grid that contains our active cubes. I'm thinking whether I should use some type of variables to denote the boundaries of the grid. where we've seen our active cubes, so that I could say like most. Yeah, so I could say most active, so in each direction, let's say in the Z direction. No, let's start with X because that's easier. With X, I can say most rightmost active cube, that would be the largest X, and then leftmost active cube, that would be the smallest X. And the same I would do for Y, bottom and top. And then in the Z, I would do the same. So that I have the most active, yeah, so kind of like the boundaries of the grid we need to loop through. This is definitely tricky, and that boundary is going to expand, so therefore on each iteration we're going to have many more cubes to loop through. That's going to expand exponentially, I think. Overall, Go is simpler language, more code to write. Oh, I see. One big diff is that Go has a garbage collector while Rust does not. Preference comes down to preference for many cases. All right. Yeah, if Go has a garbage collector, that seems more suitable in cases when you need to actively manage the memory of your program. Maybe those are use cases that are more valid for Go when you want to have more control. All right, so let me think if this approach makes sense. So I'm gonna parse the input, and then given this input, I'm gonna have to calculate a boundary. So let's do that. Let's do the parsing first. Input. Split by new line, and then another split. No, we're gonna do a map with X grid, X line, and map that X line. Yep, map each split each X line, so then we have individual elements. So now we have a 2x2, and we need to place this one in another array. So that's going to be a 3x3 now. Yeah, and we kind of we said we're going to create, it's a bit hacky to create 1,000 or 100. But we're going to have to do that because our Z is going to expand in the minus as well. And I don't feel like shifting the array. No, I'm going to have to do that. How do I create an empty array? Empty array. I think just array. I think the constructor has a doesn't the constructor have let's run our predicate grounds. This was, yeah, we can get rid of this. Array 100 empty items. So that spins up an array. We need 100 arrays, empty arrays, because this spins up one array with 100 elements, which we don't need. So I think we'll have to do this programmatically. Just gonna name this 3D grid. Apparently I cannot start a variable name with a number, so 3D grid. That's better. Okay. And then we're gonna have to Let me think. Concat. I kind of want 100. I want 100 empty arrays, and I want to create 100 empty arrays and concat those at the beginning. Because, and I kind of like pre-fill them. I could also pre-fill them with inactive cubes, but I don't have to, because I can have in my logic, I can say if it's undefined, then it's inactive. So I don't have to pre-fill them then, because that'll make it a little bit more complicated. But I do need to have empty arrays there. Because what happens if I have an array like this, it's a const array, and then I want to -1, just returns undefined. Oh, it does. Interesting. But then if it's undefined and if it's well, that's something we can work with. But what if I assign it a something? That still works? Oh, wait a second. How can that work? What's array look like? An object? What is going on? Oh, I see. So 0, 1 is here, and then so what happens is, this is super weird. Here's where JavaScript is being weird, is that it's not really assigning to the -1th element this value, but it's assigning to the just like the last one. It's an object with key -1 in that value. Yeah, that's weird. We want to avoid that in our program. Thinking out loud here. Is this something smart that I'll do? So just pre-filling the array, or maybe I could use a no. Let's I'm gonna leave that to the when we actually write the program. So I'm gonna keep that here because that's useful to visualize stuff. Let's start writing the program, and then we'll figure out how the z dimension works. And that's better. That's better. So we have a grid, and then we'll have to use. We're gonna have 4 loops, 6 loops. So that's alright. We can hard code that. For const cycle. Actually, 4 off is not the best here. For const cycle equals to 0. Let's say 1. Cycle smaller than or equal than 6. Cycle plus plus. We start at 1 and then we end at 6. Good. 6 cycles, 6 loops. And then for each one, we consider our grid. Oh, I see. I figured something out. Something clever. That so what we're gonna have to work with, we'll have hashtag or dots, but whatever is outside of our bounds, the grid that we don't need to care about in our cycle, that's gonna be undefined. So we kind of be smart about that and use that in determining where our logic should start. If it's undefined, then then do that. So we're gonna have our 3D grid here, and this is an array, and the first dimension is gonna be the Z dimension. So I can say what are we gonna use? We're gonna use map, I guess, to modify the grid. I'm gonna modify the grid in place. Well, we have a bunch of nested arrays, and those are references. Yeah, 3D grid dot. Let's do a for each for now, and then figure out what functional method we'll need to have in a bit. So Z, how are we gonna call this? Z slice. Yeah, we can call this a Z slice. Yeah, that's good. And then here's what I'm gonna do. I already figured out. I'm gonna use filter for the first one, and then I'm gonna tap into the very first. I'm gonna tap into XY Z1, no, X0 Z Y0, and see if there's something there, if there's a cube, inactive or active, regardless. If there is a cube, then we need to work with that Z slice. Otherwise, we don't need that Z slice. So that's good. That's gonna be our first functional method, and then we're gonna have a for each. Let's have a for each for now. Z slice, and inside of here we're gonna have another for loop, another loop. So let's call this for each as well. I think we need to use map, but I'll refactor that in a bit when that's more clear. So then we have Y line, and then inside there we have the Y line for each, and that's going to be our X, our cube actually. That's our cube. I hope today's puzzle is not going to be a puzzle that when you're trying to solve it with a brute force approach, like just iterating through everything, that it just takes a long time to complete. I hope today is not one of those days. We had a few days before when a kind of like a brute force approach didn't work, and you had to be smarter about how you got to the end result. You couldn't just go through every iteration and do a lot of computation, because the program would, in one instance, it would have taken me more than 8 hours to complete. So you had to use some type of mathematical formula, or find some pattern, some repeating pattern in those loops that you can just skip a bunch of iterations and be more efficient. And I hope today's not one of those days, because that's gonna make it infinitely more harder today. So we have our cube here. We're gonna have a cube, so that's good. Well, something I'm forgetting is we filtered the Z slice. So now we only have the Z slices that we have to deal with. Yeah, and I think that's gonna be our boundary. Yeah, I was thinking, do I need to filter the Y line do I need to filter Y line? But no, because we're not gonna end up with a Z line that has kind of like these undefined and the rest. No, but wait a second. So our grid is going to expand in the z direction in the minus and the negative, but it's also expand in the negative y. We need to also account for that. I need to figure out something with this because this is gonna make it more complicated if I'm not smart about this. Because y starts at 0, and we're gonna have the same thing with x. X is gonna start at 0 too. So for example here, if I'm not mistaken, this cube has one active cube. So therefore it goes inactive. This cube has 3 active cubes, therefore it stays active. So which cubes are in here? What are the cubes in here? Z0. Oh, it expanded in a Y for 1, so it's in this one. And it expanded into X. If a cube is active and exactly remains active, otherwise it becomes inactive. That's interesting. Trying to wrap my head around how they're representing this. So, okay, let's look here. This cube, it has one active neighbor. Therefore, one active neighbor, if cube is inactive, okay, it stays inactive, which is this the same cube? Z0, Z0. We didn't expand in X and Y, just Z. That's the same cube. Why is it active? If cube is inactive, but exactly 3 of its neighbors are active, the cube becomes active. Before any cycles, after one cycle. Oh, wait a second. It's not, so this is an inactive cube, and then it should stay inactive. But where is this cube represented in this iteration, in this cycle? It's not that one. It's not that one. All of those cubes are active. I'm trying to wrap my hand around how they're doing this. Let's go to another cube. This one is active and has one active neighbor. If cube is active and exactly 2, then it remains active, otherwise becomes inactive. Alright, so this cube should be inactive, which it is in all 3 slices here. This cube is active and has 2 neighbors, so then it remains active. And here all the cubes are inactive. Alright, let me see. So maybe it's in here. So even though the pocket dimension is 3-dimensional, this initial state represents a small 2D slice of it. In particular, initial state defines a 3x3x1 region. Well, it's 3x3 by 1. And then Z0. Similarly, a few cycles from this initial state produce the following configurations, where the result of each cycle is shown layer by layer at each given z coordinate, and the frame of view follows the active cells in each cycle. Here's the clue. Frame of view follows the active cells in each cycle. Alright, it's shown layer by layer at each given z coordinate. So Z0 is Z0. I think we can assume that. I think this is our, the slice we start with. This is a new representation of that slice. But something I don't understand is, let me see, is it like in Conway that all the rules are applied at the same time? during a cycle, all cubes simultaneously change their state. All right, so yeah, it's like in Conway, simultaneously. I'm just wondering why this cube, which is undefined in the z-1, z+1, so there's no active cubes there. This is the only thing we need to consider, why this cube with an inactive cube with one active neighbor, if cube is inactive but exactly 3 of its neighbors are active, the cube becomes active. Otherwise the cube remains inactive. This cube should remain inactive. Why is it active here? That's what I'm trying to understand. If you do know, so Nusa says, after one cycle, the first line becomes inactive. They don't show it anymore. Oh, really? So let's see. This one stays inactive, and this one becomes inactive. Oh, you're right. You're correct. So they don't show it anymore. Damn. All right. That's interesting. So then what we're actually looking at this is this line. No, this line. It might be somewhere else. Might be somewhere entirely else. We'll have to calculate that. But okay. So I wonder. So the way they're representing, they're kind of like discarding everything else. That's tricky. Yeah, expanding in each side. Thanks for that tip. That was exactly what's going on. I didn't understand at all. I didn't understand at all. It kind of threw me off that they just decided to. Why not just represent the first line with just dots? But I guess what they're doing here is like, yeah, like here for example, after 2 cycles, why are they representing? Oh, because this is the Z. Wait, this is the Z. Yeah, they're not cutting a slice of the Z in the X or Y, but they are cutting the Z's. So Z0, this entire area, this entire slice becomes inactive. No, because this one stays active. Cube is active exactly 2 or 3. So this we cannot discard a slice. Let's I'm gonna quickly draw it out. Inactive. That one is inactive. Active. I think now stays active. Inactive, active. I think this is a new representation of this one, right? So we have initial state. If it's active, 2 or 3 stays active. Inactive, 3. Okay. So if it's active, this one is active, goes inactive. This one is active, stays active, stays active, goes inactive. All right. So that's good. And the inactive ones. Inactive. This one goes active. This one goes active, and this one stays inactive. No, it goes active as well. Right. Wait, and this one does not go active because it has 4. Let me see. This one has a lot. No, it doesn't. This one has 2. This one has 5. This one has 3. So it goes active. This one has 1. Okay, so this is kind of like a new representation of this slice. Which I don't really see. Nusa suggests doing the last line. Last line. You mean this one? So what do we have there? That one is active and has one active neighbor, so it goes inactive. The second one has 1, 2, 3 active neighbors, therefore it stays active. And this one has 2 active neighbors, therefore also stays active. So this is, yeah, this is the last line. But my logic is flawed somewhere, because the way I'm doing it, I'm never expanding it in a Z. So I'm missing something. I will get a dot, active dot. Okay, so my last one is not correct, is that so? This cube has 2 active neighbors. And therefore remains active, unless there's more active neighbors, but there's no more Z slices to take account of. So why is the last one inactive? The cube is active. Exactly 2 or 3 of its neighbors are also active. The cube remains active. So this cube has 1 neighbor here and 1 neighbor here, which are active. We expand also in Y, but the Y is undefined here. There's no active neighbors in Y. On the first cycle, on the second cycle, yeah, after the second, but like from our initial state, I mean, you can expand this. You can expand this in every direction, but those are all inactive. Right? So those don't really matter. This one still has only 2 active neighbors. We expanded in a X now, but we can expand in a Y. It's same thing, no? And in the Z as well, there's no active. At least not from the initial state. Or let me see, wait. If a cube is inactive, but exactly 3 of its neighbors are active. Oh, I see. So, oh, I see what you mean. Oh, right. Right. That's interesting. So for every cube, I need to consider its neighbors as well. So its neighbors are in here. So we need to expand our X and Y by 1 and Z, because we're gonna need those neighbors. So we kind of like expand it in here. What we're working with, in fact, is this part. Oh, I see. So this is what we're working with. We expanded X, Y by 1 in both directions, and Z as well, but that's just going to be inactives. So therefore, what's our initial state? That's our initial state. Good. Let's get rid of this. Therefore, a new state of this C slice would be inactive. This one is active. That one stays active. That one goes inactive, I think. Inactive, active, inactive. Am I doing it right? And then maybe I missed one. We're close though. Yeah, I missed this one. Let me see. This one has, oh, okay, this one should be active. Because it has 3, right. And that one has so it should be inactive because it has 5. And that one is active, and the other one no. So yeah, all right. So we get something that looks like this on our first C slice, and then what they're doing is they're basically cutting this off because they are all inactive. And because then we have y5 and x. All right, so they're reducing, right? So they're reducing the grid by 1 in each direction, if possible. So we can shove off a 1 in the plus x, and therefore 1 in the minus. And then if we get rid of 1 in the x as well, we also get rid of 1 in the y. So you can reduce your grid to this. Let's go back and just leave it here for clarity's sake. All right, I get it. Thanks for explaining that. Appreciate it. That kind of like makes it more clear for me what is going on. So so what what I'm understanding is that this x is not necessarily the same x, or this y plane, y line, is not necessarily the same as this one and as this one. Am I right? If I'm gonna compute the z-1, let's go with z-1. What does that look like? So let's kind of like say this is z0. Let's do z-1. And z-1 is at first going to be all inactives. So then let's inactive, also inactive, active, inactive. This is tough to do in your head. This is really tough. But I guess the program can do it more efficiently if we write a rule for it. So this is inactive, active. And then the last one, inactive, active. Kind of like this. Oh, maybe I got this one wrong. Let me see. So we're looking at third y. Okay, yeah, that should be active. And then this one has three active neighbors, no? 1, 2, 3. These aren't neighbors of that one, and these aren't neighbors either. So as far as I recall, and this one, the z-plane, has all those as neighbors. This one has these 4 as neighbors. Okay, so that one is inactive, I know that. Except we're missing this one. This is a neighbor, this is a neighbor, that's a neighbor. If it's inactive, exactly 3 becomes active. That's interesting. I guess they're right. Just somehow I don't see how this one in z-1 has this one as neighbor, this one as neighbor, and that one is neighbor. That's interesting. I don't see that, but right, let's just assume I'm missing something. Therefore, so a z minus 1 is like this, which is kind of, oh, wait a second. So this one is active, but this one isn't. Yeah. Right, just like this. All right, yeah, so in here, z minus 1, they cut off, well, they cut off z minus 1 similarly to z0. They cut it off by 1 in the x directions, both dimensions, and the first two y's. So in this case, x, this x is similar, equal to that x. All right. I'm gonna do the last one as well because it's. I think it's important to know whether the first line in a z slice corresponds to the first line in other z line slices. It's kind of like essential, I think, to understand that. So I'm gonna do the last one as well, and I think the last one is just a copy of the first one. Yeah. Okay. So yeah, they are similar. All right. All right. That's interesting. Our filter is going to have to be different. Wow. Okay, so we're 1 hour into the stream and I'm still wrapping my head around this puzzle. Haven't really started coding that much. This one's a tough one for sure. For sure. But we're just gonna go on until and see how far we can get in within 2.5, perhaps 3 hours or so. I don't think I'm gonna make the stream that much longer. So yeah, we'll have to do it with that. 3D grid. So we're starting with that input. At least the music's nice. That's awesome. This tunes are really cool. I'm still deciding. I'm torn about what to do with the undefined. Do I pre-fill the array in the in those dimensions, or do I just have kind of like I have my active? I kind of like have a slice that I need to work with right now. I have a z slice and I have it boundaries in the x and y. And if I just go, if I don't do filter, let's say I don't do filter at all. Let's say I just go through each slice, which is just going to be 1. So that's good. And then for each z slice, I go to each y line, and then I have the cube. And then okay, let's put our logic in here. Cube, we need to get the neighbors of that cube. So let's get let's first get all the neighbors in this z slice. Well, let's first start with the let's first start in 1 dimension and then spread out. 1 dimension, we have the left and right neighbor. So left neighbor, or like left cube, is gonna be we're gonna either index here, y line, index -1, otherwise a dot. So if it's undefined, then we can assume it's inactive. Yep. And const right cube is going to be y line index +1, otherwise a dot. Is JavaScript going to complain if we try to access an array out of its bounds? Array 2. What is happening here? Oh wait, this is kind of like invalid syntax. 8. Console log. I don't think it does. undefined. No, it doesn't complain, so that's good. That's good. And then so we have all the neighbors in the one dimension, the x. So then let's expand in the y and get all those neighbors as well. So we're gonna have top, bottom, bottom left, top left, top right, bottom right. Maybe start with top and bottom. Let's start with top and bottom. Const top cube is gonna be, we're gonna need the index of the y line. And let me think, as the cube goes to the right, we have a different, yeah. So we're gonna do z slice index -1. So then we have the y line at the top. We can actually kind of upper y line upper. We can rename that, and then we can say z slice is going to be index -1, and then we can do y line, or we can just say not upper but top. Y line top, y line bottom, and then we do z slice index +1 there, and then we can reuse that in here, and we can say y line top at index is going to be the top, otherwise dot, and then the same thing for bottom cube, y line bottom at index, otherwise a dot. And now we need the corner cubes, so let's get top left cube is gonna be y line top index -1, otherwise inactive. I wonder if there's a shortcut to not have to repeat myself of this every time, but let's leave it like this for now. Top right cube is y line top index +1. Wait, and then we have two indices, so that's going to be a variable clash. Let's rename this index to x index, and rename this to y index. A bit more clear. Good. That's good. Okay, so then we get a bottom left cube is y line bottom, and then x index -1, and then we get a bottom right cube. I just discovered we have 26 neighbors, so that's going to be 26 lines of this. We probably can do this programmatically. Might refactor in a bit, or. Okay, so we got our neighbors in the x and y dimensions, and now we're basically expanding in a z dimension. In a z dimension, so then we're gonna have our z index, and we're gonna have z front and back, z back, we're gonna name this 3D grid z index -1, and const z front 3D grid z index. This seems right. Z back, Z front, Z slice. We can rename this to Z current or Z slice. That's fine. Yeah, Z back, Z front. All right, and then for back, we kind of need to have a loop. We kind of need to have. We need to put this in a loop of 3. Because we're gonna have different Y lines for each Z. Oh god, that's a bunch of loops. This gets nested several layers deep really quickly, because we have to do this for each. We're gonna need to get the neighbors. Okay, so let's do that for one. Z back, Z back, filter, Y line index, Y line where index equals C. Wait a second. We got our -1 slice. Okay, so then we need to get those 9 neighbors. I'm considering doing this in a for loop. Yeah, you can definitely iterate over them. It's just trying to wrap my head around. So we have our z-1, z-1 for each Y line, and then what I'm gonna do is say Z back Y line, and I need to put this inside of here, and perhaps also inside there. I need to put this all the way here. Yep. And I'm gonna need to be careful because we also have Y line defined here, so we can call this is gonna be a Y line in the Z -1. So Y line Y line Z back, Z-1. What's the best we can name this? Y line back, Y line back, good. All right, Y line back, and then if index is, so the only Y lines in the Z-1 that we care about are those that are either -1 or +1. So if index is index of current, so index back, let's name this index back, Y line back, let's call this Y index back. Good. Okay, so if Y index back is bigger than Y index +1, or let's just say smaller, -1, and then and y index back is bigger than y index +1, then we don't care about that. So we can just return, or we can wrap everything inside of there. Yeah, I'll stick to this approach. Okay, so then we are only caring about the y lines that are within one up and bottom of this cube, of that line entirely, so that doesn't matter. And then for each y line, this is so many loops. And y line for each cube back, cube, no, x index back. Amazing. All right, so then we have our cube back, our x index back, and then we only care about, again, kind of like the same logic, but for the x index. So x index back, if it's out of bounds, then there's not neighbors anymore. So those are neighbors. So now we have the neighbors in there, kind of like we can. Ooh, how about, and then we have cube back. Cube back in here is going to be a neighbor, and that's going to be 9 of them. So what we can do is we need to count the active cubes. So let's return the cubes. Let's filter. Do I need a filter? Or do I need a filter first, and then I need a wait a second. I can also slice the line. Isn't that easier? Isn't that much easier? Okay, let's go back. So we have our Z slice in the back. What we need is the Y line +1, 0, and -1. So we have it here, and then we iterate to them. There's going to be 3. It's always going to be 3. Y line back, it's always going to be 3. And then we slice this line with the x index. How about that? How about we do that? We Y line back, slice, x index -1, +2, because I think it excludes substring includes the characters that's in string. Yeah, but slice also exists on the array, so we're fine. Includes well, let's get the slice. Shall a copy portion in new array selected from start to end and not included. Okay, so we need +2. So then so we kind of mapping, yeah, we kind of mapping our Y lines. Map. This is kind of like what I'm trying to get. And then we also need to slice the Z actually as well. So maybe I can do let me think. I'm gonna start from most inside out because that's easier. We have our, let's say we are at -1. We sliced it, so we have the we have 3 elements here, 3 cubes, which we need to care about, and then let's concatenate those. We need to return an array. I'm gonna use flat map. I've used it yesterday as well. I'm gonna call this cubes for now. So this is gonna return an array of 9 cubes, if I'm not mistaken, cubes back. That's going to be all our cubes in the back. Shall we give it a try and see if that's correct? Before we go on, I'm going to add a simple console log here just so I can add a breakpoint. And then I'm going to run the debugger on our input. If it doesn't crash, property 0 of undefined, right, node day 17 today, index.js. Where is this? Line 22 in here. Can I read property 0 of undefined? Oh, because this is undefined, of course. What do we do in that case? If the top line is undefined, then we return an empty array. And then here's gonna try and tap into an empty array, so then we get a dot. That's fine. Z back, we do the same thing. What is Z back? God, I cannot type on this keyboard. There and there. Awesome. So now we should get gotten rid of the bug. Assignment to a constant variable. Of course, this needs to be let. Cannot read property 0 of undefined. Oh, because we're okay. Let's comment this part out here. All right, I think we fixed our bug. Let's let's run our debugger again. All right, so what does this look like? Cubes back. It's an empty array. Interesting. So left cube is a dot. Right cube is a hashtag. That's good. Top cube is a dot. Bottom is a hashtag. Top left, top right, bottom left, bottom right. Yeah, these are all good. And the cubes in the back is an empty array, so that's not what we want. Let's try again. Let's see what is going on inside of here. It never really gets there. Oh, because this is an empty array. Of course, this is an empty array. It never really gets there. So what we can do? Empty array. We only need to account we only need to get the active cubes. We could have cubes back is an empty array. That's fine. I could prefill it with dots, but don't care about that. That's fine. I might even get rid of the dot at no, we need to. We only care about the current cube if it's a dot, because then we need to do something else. But if the neighbors, we don't care whether they're dots. So that's fine. Okay, so cubes back, empty array, that works as expected. Can we just copy this code for the cubes in the front. Cubes in the front, and then here's C front, and then Y line back is going to be Y line front, and Y index back is going to be Y index front. All right. We've got our cubes in the front, got our cubes in the back, and then each neighbor here. Going through and see why we're not doing anything with this Y line back. Oh, Y line back, Y line front, Y line front. That was a mistake. That was a mistake. Let's run a debugger again and see. We get an empty array. That's good. What I want to know though is I want to see if it works for as we go through. So cube is that dot, yes, that, and now we are on the second line. So the top cube, top line should be the first line. That's correct. And bottom line is the line after that. So this logic seems to work out well. The Y line top, Y line bottom, and the Z back. Well, on our first iteration, we're gonna have undefined slices in the front and the back. So what I actually want to do is I want to continue until cycle is 2. Continue until cycle is 2, and then I want to figure out the cubes in the back and the front. This is all right. Okay, let's do it like this. If cycle equals 2, then let's console log the cubes in the back. Let's see what this looks like right now. Well, I'm not changing any cubes, so yeah, I'm not changing any cubes, so that makes sense. Let's I'm gonna assume this works as expected. What I want to do now is I want to count the active cubes. I want to count the active cubes. This can just return okay, so this needs to be active cubes, flat map. Well, I might optimize later, I'm gonna do that later. What I can do now is, what if I put all of these in an array? Cubes current. And then I just put that in here. So yeah, just gonna copy this. I want to have this in an array, so therefore I can count them easier, so I don't have to go through each. And I just need I don't need to assign them to a dot, because if they're undefined or if they're a dot, then I know it's inactive. So I don't need to distinguish between the neighbors being a dot or not. So I'm just going to do this by hand. Unfortunately, I'm not a pro Vim user that can do this with a few keystrokes. So just old school, grabbing the mouse, selecting, copy, pasting. And this should be a plus. Alright, this looks good. 1, 2, 3, 4, 5, 6, 7, 8. 8 neighbors. Alright, let's get rid of this part. Alright, so we have our cube's current, the cube's back, and cube's front. Let's count const active neighbors. And then we can say, let's create an array, and with cubes back, cubes front, current, cubes back. And then as we have that array, we can't do a count an array. What we can do is we can filter cube cube equals active, which is hashtag, and then we just do the length of the array. Alright, console log active neighbors. And what else are we gonna log? We're gonna log the z, x, and y. So z index, y index, and z, y, and x, and also the actual cube, and then the active neighbors. Alright, so let's go through this. And I'm gonna just go one cycle here. Just one. Okay. Alright, so what do we have here? We have the z index, which is only one slice, so that's good. Then we have the y, we go through each y. That's good. And then for each y we have the x, and then the current cube at that position is that one, and this one has 2 active neighbors. Let's kind of like see. I'm gonna go through a few of them by hand to see if it's correct. This one has 2 active neighbors, that's good. That one has 4, that's good. This one has 5, no 4, yeah 4. This one has 5, 5, 4. So far so good. This looks good. Yeah, I think we can implement our rule then. So the rule was if the cube is active and if there's 2 or 3 active neighbors, it remains active. Otherwise we change the cube. So if an active cube, if cube is equal to active, and let's put this between parentheses, if active neighbors is otherwise the cube becomes inactive. So if the active neighbors are smaller than 2 or active neighbors bigger than 3, then we modify the cube. Otherwise we just return the cube, kind of like, I have to figure this out in a bit. And then else cube is inactive here, and we're gonna have another if cube is inactive but has exactly 3 neighbors, then it becomes active. So active neighbors equals 3, then we change the cube. Otherwise return the cube, so that's good. And so in here we want to say return a dot, and here you want to say return a hashtag. So this cube becomes inactive, and otherwise in here it becomes active, and otherwise return the current state of the cube. But what are we actually returning here? We are doing a for each, so that's not going to do anything. Let me think about this a bit. Are we gonna modify the grid in place? So just do map, 3D grid map, and then on each iteration modify the grid, or maybe create a new grid. Do we want to create a copy? Perhaps we might want to create a copy. I'm thinking about this. What's the smarter way to go about this? Because we are gonna change on each cycle, we are changing the grid, and that grid we're gonna have to use on the next cycle. We don't care anymore about the previous state of the previous cycle, the state of the grid in the previous cycle. We don't care about that anymore. So we're fine with modifying it in place. We're fine with modifying it in place. I'm gonna just make a copy. But it's gonna have to be a deep copy in 3 dimensions. Great. How about this? How about I just don't complicate myself? Pull this to the first part, 3D grid. We're gonna have to figure out, we're gonna split it. Yeah, we're gonna do the same thing for the second part, so good. We are good with modifying this in place. So instead of returning, we're gonna say 3D grid. Oh, but wait a second. I almost forgot something. Is that we can't modify this yet because it's gonna change for the next cube. So we need to keep a current copy. So we need to modify a new copy, next grid. So we can say 3D grid is that, and then we can say let, or it can be a const, whatever. It can be a let. Yeah, next grid, next grid, next. The grid, that's just gonna be nothing now, but we're gonna assign it to this const next 3D grid. There we go. And then here we're gonna use a map eventually. So wait a second, let's here return byline for each cube. This is a map. And then return, this is a map as well. And then return, and that's a map. All right. So let's see how, that's interesting. This line is unused. Oh, there. So let's figure out, I'm gonna leave this here. Let's figure out how our slice looks on after the first cycle. I'm gonna add a for breakpoint here. Okay. No, it needs to be here. So here we're at cycle 1. Now we're at cycle 2. Okay, so next 3D grid, it's in here. All right, what do we have here? So this should be a 3D grid. So these are let me think. This should be right. So we only have one slice here because there's only one element. So we need to fix that. But this is one slice, which is, I guess, the current slice. Yeah. This current slice is modified into this. And if we go back to our example here, this current slice got modified in that, so which is what we did. Let's go through it and see if it's correct. This one stays active. This one becomes inactive, so that's good. This one becomes inactive, 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 stays active. Yep. Becomes active, correct, inactive. All right, so yeah, this looks good so far. I think that works. Let's fix our Z slices. So we need to get more elements in this 3D grid because whoa, what are we doing here? We're mapping. We are mapping. Let's get rid of this filter here. So we need to map, if we have another array here, another array at the end, it's going to go through that as well. But this needs to be dynamic. I don't know how many arrays, how many Z slices are going to be in the back and in the front. So here we're looking at a 3D grid. This is Z-1, Z0, Z+1. If we manually add it, then it's gonna generate, I think. Still empty. I think we haven't really accounted for the fact that yeah, so I'll somehow need to pre-fill these arrays. I'm thinking of a simple approach to just pre-generate the grid about 100 in the Z-100 and Z+100. Oh, but wait. We're gonna face the same issue for the X and Y. Alright, that's an interesting problem to solve. Now, our code is working, but it's just taking the current input slice into account. It's not it's not looking for inactive cubes outside of this grid. So at the boundaries, and then it doesn't turn those into active. So that's what we need to solve right now. Is we need to have, I mean, we could expand our boundary by +1 in each direction, because we don't care more about more than that. So I guess what we could do is maybe we can have some logic in here that says before we iterate on this grid, we need to have the grid expanded by 1 in each dimension. And then we're going to need to compute those as well. Let's do that. Let's try and work with that. Let next 3D grid. There. We're going to say next 3D grid. equals equals grid, just assign them to each other. And then next 3D grid is this is a tricky one. So what I essentially want to do is I want to expand it in the X direction, in the X dimension with plus and minus 1. I want to expand it in a Y dimension with an Y minus 1 and Y plus 1. And I want to expand it in a Z, in the depth dimension with a Z minus 1 and Z plus 1. So let's start with the X. Let's start with the innermost one. What do? I have an array with how many? With 8 elements, and it needs to be 10. It needs to have, oh, okay, I can use splice to insert a dot in each. Was it splice? Removing or replacing existing elements and or adding new elements in place. So that's what I want. Let's let's do a for each. Today's solution is very loop heavy, a lot of loops. So we have here the Z slice. Then we have C slice for each. We have the Y line. And then Y line for each. Oh wait, we don't need to loop again. So we have the Y line, and then therefore we add Y line is equal, well, we need to map. Let's map Z slice for each Y line map return splice. I need to insert a dot at the beginning and at the end. Start the index at which to start changing the array. If greater than the length of the array, star will be set the length of the array. In this case, no element will be deleted, but the method will behave. Wait, I can just do this. Wait, this is much, no, I know. This is much easier. I can just say dot here, spread it out here, and a dot there. There we go. That's much easier. So we do that for each Y line, and then we need to map. We need to map the Z slice as well. Map C slice, and it needs to return kind of like the same thing. And C slice, but this needs to be filled with dots. Wait, so we added a dot for each X, and now we need to add a dot for the Y. So that's what this does, I guess. Yeah. Let's pre-fill this with dots. How do I pre-fill something with dots? How do I create an array? Oh, fill. Awesome. Array fill. Fill. Can I just value to fill the array with? Awesome. Nice. So I just create an array dot fill with dots. Nice. This is what I want. This is what I want. Fill with dots. This is good. And then we have our Z slice in here. So we can just const new Z slice. like this. And then for now we're going to need to create new two Z slices, one in the back and one in the front. We need to add it to the grid. So we're going to say next 3D grid is going to equal our next 3D grid in here, spread out, and then we're going to have a Z slice in the back and Z slice in the front. That's interesting. Let's create a Z slice. Maybe I create a function for that. Maybe create a function for that, because it's gonna be a slice filled with, so it's gonna be this fill with dots, but then wait, how does it know how big it is? Oh, okay, let's create it. How to create an array with an X length in JavaScript? I never have to do that. Create an empty array. Let's I think you just do array 10 empty items. Good. So how big does this need to be? This needs to be as big as this line. So array y line length. So create an array with the length of this line, and then we fill it. Yep. Same here. Same here. And then same here. I'm gonna add comments later. Maybe I add comments now. Add empty lines in the y dimension. Add empty cubes in the x dimension. And what I want to do here is add empty slices in the z dimension. Thank you for following. It's Code Life. Appreciate it. Thank you for watching and giving me a follow. Very nice. I think I've reached. You're the 10th follower, so it's a milestone. And so we have the z dimension. All right. And let's add empty slices in the z dimension. And what I need to have is I need to know how wide the pane is, I guess. So how wide the slice is. So I need to know the y length, the length of y line of a z slice. So maybe I can do 0 and then 0 and then length. This is way too ambiguous, but let's see if it works. I deleted my 3D grid example here. That's a shame. But here we're in the y. Yeah, this is the y. So that's the length. Create an array. I might extract this into a function a little bit if it gets too hairy, and then create variables so it's more easy to read. So create an array and then fill that array. Oh, this is a bit hairy, to be honest. Okay, so what's happening here? We create an array with as big as the y line, and then we fill that array with dots, And then we need to do, so we created in a new Z slice, we created one line, but we need to do that for as long as the Z slice is length. Let me create a function, create empty slice, and it's gonna take an input. I don't know what the input's gonna be yet, but oh, maybe I know. If I need to create a Z slice, I need to know how far it goes in the I and in the X. So I and X. X length and Y length, and then so we're gonna have our Z slice, and this is gonna be a this is gonna be an array of Y length but we need to have, let's use a loop. I'm gonna give Y a better naming, or I might not, I'll see. But for now, let's stick with I. So I smaller than length. So we go and then create an array of X length and fill it with dots. And then we have our Y lane. So we can say const Z slice here, and then we can concat or push Z slice. Yeah, I'm gonna push it. Push in there, and then return Z slice. I think that should cut it. Let's run this in the playground, see what it does. Console log, create empty slice. Let's say the slice is gonna be 8 by 8. So what do we get here? We get a Z slice in which this is a Y line, and inside that Y line we get 8. Looks good. And it's 8 of them, right? 1, 2, 3, 4, 5, 1. These are 4. That's another 4. Yep, looks good. Yep, I think this works. So we can use here, instead of this, we can say create an empty slice. And then it's gonna repeat again, and it's gonna need to have the X length. So we can just say 0, 0, 0 length, because that's the X, and then perhaps do this over multiple lines. Like this, and the Y length is gonna be kind of like the same, but this one less 0 tab. Okay, let's copy this, move to the bottom, get rid of this. All right, so hopefully this does what I think it does. a helper function to create an empty slice in the Z dimension. Good. All right, so I hope this does what it does, and therefore here we have the we expanded our grid, so then our rules should take into effect for that grid, and we do that every time. Okay, I'm just curious to run the program, and so our answer is on the last cycle we're gonna have our grid here. So I'm just gonna run the program and see what the final grid looks like after 6 cycles. Yeah, I can log it here. All right, moment of truth. Might just first a few errors to fix, of course. There's always errors. 17, line 17. Y line is what? Not defined. What? 17, column 19. That's here. Y line is not defined. Oh wait, this is outside the loop, of course. Z slice 0. Yeah, that's what we want to have. Let me put this in multiple lines as well. Yep, this is gonna be defined. Okay, next error. No more errors. Okay, we get a grid. It's kind of hard to read like this though, so I'm gonna use the debugger instead. Add a breakpoint here. I'm really curious to know if this is the right answer for us. So this is our final grid. It looks we have 12. We have 12 slices in the Z dimension, and then our biggest Y dimension. So in the 6th, kind of like in the middle of our Z dimension, we have the widest or the largest in the Y direction. Yeah, that's interesting. All right, I'm just gonna count the active cubes and see if that's the correct answer for the first part. We spent a fair amount of time for the first part, so hopefully we're there. Let me make this a little bit bigger now. So what do I want to, so I have our grid here. I guess we have to loop through the grid. Const sum. Sum of active cubes. And then we have our grid. And then we're going to say reduce accumulator, and then we have our Z slice. And this is going to return accumulator plus Z slice reduce. I could just flat map everything and then do a reduce. Might be easier. Let's do that. Maybe not. No, we're gonna stick to this. We're gonna have another accumulator inside. Really. And then we do Y line. Then we have the Y line, so then we could just, what can we do here? We can filter a cube, and then cube equals to X, and then we have our y line, so that's length. Great, and then we add accumulator to that, so accumulator plus the length, and we instantiate this at 0. Okay, this might be it. Console log answer part 1. Sum of active cubes. The moment of truth. I think first we're gonna have an error. No error, but we get 0, which is not correct. Oh wait, capital X, not wait, not X. I'm confused with a different day. Hashtag 3. So that's not correct either. We have our y line. Oh, that's because we're only going through the first y line. Are we? So we have our 3D grid, then we go through each slice and we reduce each slice, and then we have each line, and then we filter each line with the active cubes, and then we get the length of that line, and then we add it to the accumulator, and this should return the total for that slice, which we added to the accumulator. We should return, let me think here. We have slice, we have line, and a line is gonna be filter. We use filter for the cube. We only get 3. I wonder, is that because let me create another variable here. I'm gonna say there's active cubes in active cubes. Yeah, that's good. C slice, and then let's assign this to this. Maybe the bug is gonna become clear if we make this a little bit more readable. We reduced, we have our grid, we reduce each C slice, we count them up, active cubes, alright. And then for each C slice, we have another reduce. Alright. And then here, let's return. And that's, let's call this const active cubes in y line, and it's going to be active cubes in z slice, or just in z, that's fine. Active cubes in y, and then let's assign this to that, and then return that. Okay, so is the bug more clear now? We are here, we have a y line, which is going to be like this, and then with filter, we only keep the active cubes, and then we get the length of that array, which is going to be the amount of active cubes, and we add that as we go through each line in that slice, and then we have the total number of active cubes in that slice, and then for each slice we add the total number, and we should get the sum of active cubes. Maybe this logic is correct. Maybe let's have a look at our final grid. Maybe the grid just has three active cubes, so then something is wrong in our grid calculation. Yeah, this one is empty, this one is empty, this one is empty. Looks like our grid only has 3 active cubes. These ones. Kind of like the middle Z slice, and everything else is inactive. Okay, so there's a flaw in our cube logic. in our rules at the top. So this is all correct. We can leave it like this. Let's go to the top and figure out what is amiss here. So if cube is active, switch around. If cube, we already tested this logic and this seemed fine. Active neighbors is 3, then turn that cube into let's see, what I want to see is on the first iteration how our grid looks like if we did the expansion right in each dimension. So I'm going to log that. So here's our grid, local, next 3 grid. So we have our Z slice in here, which is, oh, I see what's wrong. We have our Z slice in here, which we've added, which we expanded in the X and in the Y. So we should have X length of 10 and Y length of 10. But then here we have Y length of 8 for the Z slices in the back and the front. So for some reason, this length is not what we... So the Y line is expanded. Oh, I see. That's because we've expanded our Y line, so this one should be new Z slice. There we go. And so let's run it again, see if it's that did the job. Yeah, all right, so we have each Z slice is 10 in length, but each line just has 1 element, so the X is not good, which is the inner. So this, each Y line for the first slice, initial slice, it's 10 X wide, which is good, but it's only 1 X wide for the copies. So we somehow messed up the length of, let me see, the X length. Here we're tapping into that next grid, 0, 0. Maybe it's just oh no, this needs to be, I'm off by 1. This is the line, and therefore the length of the Y line is how far we go. This is a bit confusing. Let me rename this to X wide and Y long, X wide, Y long, kind of like that. So X wide is the length of Y, and Y long is the length of, yeah, of the slice. That's good. We were off by 1 here. I assume, let's run it again. Yep, this looks good. We have 10x for each one. Awesome. So now let's run our program again and see if that was indeed a bug. Still 3, so that wasn't it. So our grid looks good now. Let's have a look at the grid. Our grid is like this, so it's the Z slice in the back is all empty. In the front is our initial one, expanded by 1 in the x and y, and z in the front is all empty. Alright, let's go one cycle, see what happens. So in our next cycle, this is our original slice. Yeah, this is our previous slice. Okay, so what we can see here is that the slices in the back aren't modified, and the ones in the front aren't either. So somewhere in our logic in here, we're not modifying the Z back, Z front. Let me see. Let's add another debugger in here and go through it. Z back, Z front. Oh, I see what the problem is. I'm using 3D grid here to grab the Z backs in front, but I should obviously use the current one. Yeah. All right, let's give it another spin. All right, so Z back is indeed empty, but Z front is our current slice. This looks promising. I'm gonna run the program again, and I get 100. I'm just gonna guess. I don't think it's right. 100 seems too low, but too low. Yeah. So we haven't fixed our solution yet, but we're getting close. We got from 3 to 100, so this looks promising. So then we have our Z in the front. Our Z in the back is empty. Our Z in the front is that, which is our current pane. Yeah. And then go in there. So let's see, after we modify this one, we should get like a couple of active ones. Let's see what happens after we modify the current pane. So what's our back? Well, that was empty. That was okay. So how do I get? And that's gonna be front, and then it's gonna be next cycle. Okay, so now we modified our, still empty for some reason. And then here we only have a few changes, but yeah, so that one is still empty. Let's go inside here, and I'm gonna say, so Z slice. Oh, I see what's wrong, I think. Not yet. So we get our back and a front Z slice, and then what are we doing here? Would be useful to add some comments. If me 1 hour ago would have added comments in here, it would have made myself, current me, much easier to debug this. Grab slices at Z minus 1 and Z plus 1. All right, and then this is the current slice. We map it. That's good. Current slice, Z slice is mapped, return. Good. Okay, grab lines at Y minus 1 and Y plus 1. Y line top, Y line bottom, and then we map the current line, and then we go into the line. That's good. And then we have the cubes back. Okay, so maybe this is our bug. Wait, let's not jump ahead. So we are in the current line. Okay, so we have the neighboring cubes in our current Z slice. And then we grab the cubes in the back C from the previous C line, C slice, which is Z back. It's good. And then inside of there, and then we grab the cubes in the front. I'm gonna add a breakpoint here and see what's happening. If I can wrap my hand around, where are we're gonna stop at cubes in the front is empty, cubes in the back is empty. Maybe our slice here is wrong. So our Z back is empty and our Z front has this. Okay, so there's definitely what's our Y line? Our X index is 0, or Y index is also 0. We're at the first line. Active neighbors. Let's look at the Z in front. Active neighbors for this one. This one has one active neighbor, which is bottom right of the Z in the front. And we don't grab it. So our bug is somewhere inside of this function and probably in this one as well. Breakpoint in here. Debugging this is really tricky. It's really tricky. Y line in the front. Okay, so that's our top line, and then we should go the next line. Yeah, so there we have our active. So we slice it. We slice it by the X index, which is 0, minus 1. Oh, wait, I see what's wrong. If slice grabs gets a negative number, then it's gonna go at the end of the array. So we want to avoid that. Let me think, because what we're doing here, this needs slice, these shouldn't go into the negative. X index. Let's perhaps create some variables. So what are we doing here? We're slicing the line from the left and the right. So then we say left limit is X index minus 1, const right, or bound, not limit, bound is a better naming. Left bound, right bound is X index plus 2. And then we're gonna use these here, but then we gotta watch out that these need not be negative. So if X index is 0, so then we reach the far end of the left side, then just return 0, otherwise return X minus 1. And if X index is equal to the length of the line, length. So when did we reach the right bound? If X index Y line length minus 1, yep, is equal, then just return X index, I guess. Otherwise return X index plus 2. Let me go through this again, because I don't want to be on off by one error and have to debug and spend a lot of time debugging this. I'm gonna double check that the logic is right here. if we reach the right, if the current cube is at the rightmost cube in the line, so y line length minus 1 equals x index. Where's index? X index come from here. Yeah. Then return x index. Otherwise, then we're gonna be minus 2, return plus 2, excluding. Okay. Seems good. And we're gonna need this as well for cubes in the back. We could refactor this and make it more dry to not have to repeat ourselves here. Y line front. Something's amiss. Y line front. Y line front. Y line back. Why is it Y line back? Oh yeah, Y line back. Y line back. Okay. Got it. Got it. Left bound, right back. Y index back. Oh, this needs to change. Y index front. Oh no, this does not need to change. X index is still the one we care about. Y line. Oh yeah. Y line back. That's the one we care about. Y line front. Yep. So where are we using this Y line front? We're using here to get the bound and then slice it. And then Y index front, we use it here to kind of like return an empty array. And so same here, we use it there, and we use this one here. Okay, this looks good. Let's run it again with the debugger. So our Y line front is gonna be that, and then Y line front is gonna be that. Okay. So if I add another debugger here, do I get the cubes front? Yes, I do. That's good. And then here we're kind of like doing a filter. Wait a second. Cubes front should return the neighbors in the front side, which is at most 9. Why do we get 20? That ain't right. Left bound, what does slice do? It's up until excluding, right? Start and not included. So left bound is -1 start, and upper bound, right bound is +2. -1 +2 which is going to be -1, 0, +1, and excluding +2. This looks good. Cubes front. We still get a bunch of cubes though. Maybe this is wrong. So Y index front is smaller than Y index. Okay, so because what we're doing here, this is our Z front. So the only active cubes we should get should be this one. For the yeah, because wait, what's our X index? 0, Y index 0. Yeah, so the only cubes front should only be the active. Well, at least we should get these cubes, these ones in here. So we should get 4 cubes, and not all of these. So somehow Y index front, if it's smaller than Y -1, let me see. Oh no, wait a second. No, that's good. So our Y index is 0 -1, Y index front. 0 minus 1. Let me add a debugger here. Wait, run again. So we have our line in the front. Up there it's all empty, that's good. Index is 0. Index 0, 0 minus 1 is 1. Is minus 1, which is smaller. And what is this logic? So this logic says, let me add a comment to this logic. Discard lines, discard lines in the y dimension that are beyond, discard lines in the y dimension that are beyond, that aren't adjacent to the cube. Discard lines in the y dimension that aren't adjacent to the cube. So that's what this is supposed to do. If y index of the cube minus 1 is bigger than y index, or y index plus 1 is smaller, no, it's bigger. So if the y index of the cube, so that's 0, y index front, zero smaller than, is 0 smaller than minus 1? No. Is 0 bigger than 1? No. Therefore it's false. Let's add a breakpoint here. Let's add a breakpoint here. Yeah. I think. Wait, let's add a breakpoint there, Okay. Okay, so for the first one, we should go in here, I think, because 0 is not smaller than minus 1 and 0 is not bigger than 1. So we should go in here. That's good. Y line in the front. This is, I'm so deep in this code. This is so hard to debug. Which I expected dealing with three-dimensional arrays in code. Let me see. Y line in the front, so we get our left bound, our right bound is 2, 0, 2, and we slice it. So the Y line in front, we slice it, 0, 2. So Y line front, if I copy value, and then if I slice it, 0, 2, what is that going to return? It's going to turn, yeah, that's good. All right, next iteration. We have the next line at the bottom, which is at index 1. Index 1 is not smaller than minus 1, so that's good. Index 1 is not bigger than 1, plus 1. So then we should go in here. Yep. So left bound is 0, right bound is 2. We slice the line. That's good. And now we have line 2. 2 is not smaller than minus 1, but 2 is bigger than 1. Therefore, we should go in here. We don't. Or. Oh, this needs to be an or. This happened to me so many times. All right, let's I hope that fixed it. Let's add an OR here as well. So now for cubes, so now cubes front should be yes. That's exactly what cubes front is. And then active neighbors is 1. Okay, let's run our program. Hail Mary, 448. If this works, I mean, it is, oh, awesome. I mean, obviously I know what the program does. I understand what the program does, but also if it didn't work as expected, I also didn't really understand what went wrong. So yeah, but it does, it worked. You saw for the first part. Celebration. That's cool. All right, part 2. We are 2.5 hours into the stream, a little bit over that. Are we going to be able to solve part 2? Oh, there's a bunch of text here. All right, so let's get reading. Part 2. For some reason, your simulated results don't match what the experimental energy source engineers expected. Apparently, the pocket dimension actually has 4 spatial dimensions. Holy shit, no, that's way, no, that's, no. Nope. No, negative. My brain cannot do this. Part 2. Okay, let's keep reading. 4 spatial dimensions, not 3. The pocket dimension contains an infinite 4-dimensional grid at every integer 4-dimensional coordinate x, y, z, and now we have w. 3. There exists a single cube, really a hypercube. I was reading about hypercubes a few months ago. Just trying to understand them was really difficult, let alone programming and dealing with them. Which is still either active or inactive. So at every integer 4-dimensional coordinate, there exists a single cube, which is still either active or inactive. All right, so each cube only ever considers its neighbors. So any of the 80 other cubes where any of their coordinates differ by at most 1, for example, given the cube, blah, blah, yeah. So now we have 80 neighbors for each cube instead of how many we had now? 26. We have 80 neighbors. The initial state of the pocket dimension still consists of a small flat region of cubes. Furthermore, the same rules for cycle updating still apply. During each cycle, consider the number of active neighbors for each cube. For example, consider the same initial state as in example above. Even though the pocket dimension is 4-dimensional, this initial state represents a small 2-dimensional slice of it. In particular, this initial state defines 3 by 3 by 1 by 1 of a 4-dimensional space. Simulating a few cycles from this initial state produces the following configurations, where the result of each cycle is shown layer by layer at each given z w. So z0, w0, we start off with this, and then after one cycle we have z minus 1, z0, z1 for w minus 1, and then we have a repeating for w0 and repeating for w1. Damn, this is really tough. After the full 6-cycle boot process completes, 848 cubes are left in the active state. I guess we could use our example input to test our code. New file, import2.txt. Move this to the right. There. That's going to be our example input. And then let's work with the example input. Starting with your given initial configuration, simulate 6 cycles in a 4-dimensional space. How many cubes are left in the active state after 6th cycle? So wrapping our head, debugging this is very difficult, because with another dimension in play, it's really tough to understand what is going on. But program-wise, we can just copy the solution here, and we just need to add another dimension. We need to take into consideration there's another dimension. Let's try and do that, see how far we get. We might have to shut this to wrap this before we reach an answer for the second part. I might have to wrap the stream, but let's see how far we get. I'm gonna put all of these code in an IIFE, which stands for immediately evoking function execution, so that all the variables there have their own scope. And I'm gonna do the same for the second part, so that we can just copy the first part in here and not have to deal with variable name collisions. All right, so here's our second part. Yeah, well, now we have a 4D grid. 4D grid. And our 4D grid is let's rename this as well. Next, 4D grid. It's an array, but that's an array as well. That's an array as well, kind of like this. Yep. So still we have 6 cycles. So next 4D grid, the first iteration is gonna be W slice. So let's call this W slice, and then inside of here we're gonna have W slice map, and then we're gonna have a Z slice. So let's put everything that we have in here up top, and then let's return this. All right, so we still need the same code for the Z slice, but we need a new V slice, new W slice, and then just return here. It's gonna be a new W slice, and we kind of need to do something similar to this. We need to create a how about, well, this is a bit confusing now because I named slice the Z slice. Maybe I call W pane, because an X is a cube, a Y is a line, a Z is a slice, and a W is a pane. A pane is synonym to slice, so no. So let's just rename this then to create empty Z slice, and then we're gonna create another function that is gonna create an empty W slice, and it's gonna use this one to create an empty slice. Okay, so let's up top here, function create W slice, create empty W slice. And this helper function to create an empty slice in the Z W dimension. So what do we need to know? We need to know how, for the Z slice, we wanted to know how wide the X and Y. For the W slice, we need to know the I have no idea, because I don't understand hypercubes that well. Well, for one, I do know, so we have those Z-slice in here. Can we just somehow copy and figure out where it needs to be? So W slice is gonna be a bunch of Z slices. So for let I y long, so instead of y long, we do Z, but it's not long, it's Z x, Z length, let's do Z length. But it's not gonna be the length of Z, it's gonna be the Z wide, so x. So a Z slice is 2D. It's x wide and y long. A W slice is gonna be x wide, y long, and Z deep. And then for and then here W slice push, we're gonna call our helper function from here, which we can move to the top. Oh wait, there, move all the way to the top, and then we're gonna call this function, we're gonna pass it in, we need to pass in how wide and long it is. So maybe we get that from here. I'm not sure. And Z deep, we're gonna need to get it from here as well. So x wide, y long, and it needs to be filled. We get an empty slice. Yeah. So we create empty slices for how many empty Z slices, how many Z deep the W slice is. And how do we know how deep it needs to be? Let me think. Or I guess we know that it's gonna be similar to this. Our code is gonna be similar to this. So let's no, wait a second. We need to nest this inner side. So add empty cubes in the X dimension, add empty lines in the Y dimension. And here we need to, I think I can just return this. Add empty slices in the Z dimension. Is that right? New Z slice. New Z slice, return new Z slice, the length of that one. Okay, then we have our new Z slice here. And now that's our new W slice. And then we need to create an empty Z slice. So add empty cubes. All right, we mapped that. We mapped the Z, add empty lines. Right, so then we map the W by adding empty Z's, empty slices. And then we use the, I think this is all good. No, we need to, yeah, that's gonna be in between our new W slice. And we need to add those at the top and bottom. So then next for grid, is that what we wanna tap into? I don't think so. I think it needs to be W slice, new W slice. And inside a W slice, we get the Z, and then the so what is the function expecting? X wide and Y long. So here we have, this is the first Z slice of that W slice, and then this is going to be the Y, and therefore another one is going to be the X. And then here again, another one is going to be the Y. Okay, this should do it. And then here at the end, we're going to create empty W slices in both directions. And we're going to do new W slice. Oh, this is next for grid. Really grid, okay. And then here, so what are the arguments? X wide. This is a bit confusing because Z, Y. So let's mix these. Y long. No, actually I'm not gonna do that. I'm gonna stick with it like this. X. So and then we, in our grid, we have X. And then we have, I'm definitely gonna refactor some stuff, add some comments later on to make this more readable. And then here we need to, the length of the Z, which is this. There we go. So I think this should do it with our grid like expansion. So this is all grid expansion. We have two helper functions, and then we expand the grid here. Expand grid in Z, Y, and X dimensions. And here we expand the grid. Expand grid in W dimension. All right, so now to our logic in here. Next 4D grid, well, that's gonna be a W slice. So we're gonna have next 4D grid, this is gonna be W. All right, yeah, and then I need to get a bunch of neighbors, a ton of neighbors. Oh my God. Yeah, that's really interesting. I'm gonna wrap it up because we are almost 3 hours into the stream, and I'm not gonna be able to solve this within 3 hours. There's still quite a lot of logic to work on. I'm gonna work on this off stream, and I'm gonna, so this is not very, conceptually this is not very hard. What we need to do here is we already took an account for the extra dimension in creating when we expand the grid, which is all of this basically. all of that code expands our grid on each cycle. But what we need to do now is inside we're gonna need to grab the neighbors. So instead of 26 neighbors, we now have 80 neighboring cubes because of the extra dimension, and we're gonna have to add the code for that in here by just, this is gonna be a W slice, and then in here I'm gonna say return W slice map Z slice, and then W index, and then everything here is gonna go in there. Oh, and then in here we're gonna have some logic that we're gonna have to say grab slices at W minus 1 and W plus 1, and then we're gonna use those, and that's gonna be, I guess, just const W back, or not back, because now we're not going back and front, we're going to a 4-dimensional direction, so that's gonna be W W, yeah. But in any case, so we're gonna have to grab W's in each direction, and then for those we're gonna need to grab the Z's. So we're gonna have a loop in here. I think this is gonna be, yeah, this is gonna be outside. It's gonna be outside here, and then inside here, this is gonna use W slice, and then we're gonna have more of these, and more of Y lines, and more of current neighbors, and more cubes, and so on. And all of that changes. Our active neighbors is going to be a bigger list. This is going to be the same, the filter and the length, and the rules are also the same. So this is going to stay the same, and then we modify the cube. So that's kind of like what our solution. Some adjustments here, and then our answer for second part is going to be sum of active cubes. This is going to change as well. We're going to have another nested reduce in here for the W slice, and our answer for part 2 is going to be sum of active cubes. Let me do just that before I wrap up the stream. So this is W slice const active cubes in W is going to be W slice reduce accumulator Z slice there, and then we can move this to the top, and then here return accumulator active cubes in V. Yeah, so we just nested that, but it's yeah, so that's kind of like the same, just a nested loop inside, one more loop, a bunch of loops in this solution, and yeah, so now I just need to solve to kind of like adjust for the extra dimension, for the W dimension in here, starting in here inside, and that should be the solution for the second part. I'm gonna do this off stream. I'm gonna push the I'm gonna commit the code and push it to the repository so you can have a look later. So keep an eye on this repository. Let me link in the chat. Click into the chat. There it is. Later today, I'm gonna have the answer for the second part as well, and I might go over it tomorrow morning to explain if something significant changes. I'm gonna go over and explain, but basically it's just as I explained it now. The solution for the second part is just changing this logic in here to account for the W slice, which is basically just nesting, adding another nested loop, and that's that. Yeah, thank you for sticking around. Appreciate it. Thank you for watching. I hope you enjoyed watching this. At least we solved the first part, which was cool, but today's puzzle is definitely a tricky one. Thank you for watching, and I hope to see you tomorrow, same time, 10 a.m. Central European Time. We're gonna go on with day 18 of Advent of Code, and we're gonna continue. And yeah, see you then. Bye bye, have a nice day.